4.9 static friction and 4.10 friction in inclines. I might say 4.10 part 1. I'm going to decide if there will be a part 2, or there probably will be. Okay, but 4.9 is very short. That's why I wanted to put those two together. Okay, first static friction and then the incline stuff. Now, static friction, there's an equation for friction. I already told you this. You see mu K F N. Well, the little k means kinetic friction. Kinetic friction. And then there's also something called static friction. Static refers to something being at rest, not moving, in relative to you, and then kinetic means it's moving. Well, the main example of this is the one that I've always mentioned already, maybe 2 times or a couple times before. Say there's a really heavy box on the floor, like on a make it like a tile floor. So it's like, you know what, I could push this box, or how about concrete floor, like at a garage. You got a really heavy box there. You got to move it to your car. Well, instead of carrying it, it's I'm just going to push the thing. So you're going to try to push it all the way over there, and then at the very end, you'll lift it up near the end. Somebody will help you or whatever. But have you noticed this, that it's easier to keep an object moving when you're sliding it across the floor? It's easier to keep it moving than to get it in motion to start off with. Now, I can't really, I can't think of a way to show you that here, but I'll say it to you, and then you can always try it yourself. But like, here's a book. I don't know if I have anything heavy enough to use for it. Well, I guess I have this box of molecule set here, but all I'll say is, it's easier, like if I want to get this thing moving, and we could even use what's called a spring scale. Like you pull it, and it's like, actually, you know what? It's the same thing they use to measure luggage, like a luggage scale. You hold it up, and you hang it, and it stretches a spring. Well, you can take that and you can put it on here, and you can pull. This would be great to do with luggage, actually. But what you do is you say, okay, I want to pull this luggage across the floor. Like put it flat on not to harm the floor, but I'm going to pull it, and I'm going to pull that spring, and you'll notice, like, just say if it takes, like, it'll start moving. Let's say, just say, oh, it starts moving when I add 4 pounds of force, okay, or I'll make it 5. At 5 pounds of force, this thing will start moving. It'll be at rest, but I'll pull it, I'll stretch it, and once you get to 5 pounds of force, that thing starts to move. Okay, well then here's the weird thing. So you can stop it, and every time you pull, when it starts to move, 5 pounds, it starts to move. You can keep doing that. Well, here's the weird thing. Once it's already moving, you don't have to add 5 pounds of force anymore. Once it is moving across the surface, then you only need, like, maybe I'll just make up 4.8 pounds, okay, are needed to keep it in motion. So 5 pounds will keep it moving. Now, I'm sorry, 5 pounds will start it moving. 5 pounds can overcome static friction, but then you only need 4.8 pounds of force in order to overcome kinetic friction. So maybe that isn't the best example, whatever, to show it with that, but it's like saying, well, I could draw a little friend here, a little girl here, Lily, and just say she's pushing this box, this real heavy box. She cannot get it moving at all. She can't move that box across the floor. She's too small. It's too heavy. But if somebody else comes along and says, hey, I'm going to help you, and they start pushing it with her, and it starts moving, now that person can start it moving with her, run alongside her, and she gets moving, and then they can walk back, and she'll be able to keep it moving all the way across the floor. Because a small force is needed to keep it moving, but a larger force is needed to get it in motion. Okay, well anyway, the equation is kinetic friction here, and static friction is mu s Fn. And so there are different coefficients for what they call static friction and kinetic friction. Okay, so here's a picture, and it says, Happy the seal is lying still on the frozen ground. So I'm going to draw a little picture of Happy the seal. All right, he's happy, so make him happy. Happy. Okay, there he is on the frozen. I'm going to make him more flat so he has a little bit more friction. And here's the frozen surface. So it'd probably be pretty easy to move him on that. But okay, we can make it. We can say it's not real slick, not smooth. The ice is kind of rough, whatever. So all right, Happy is there. Oh, it says frozen ground, not ice. So frozen ground, yeah. So what force is required to keep it to put him in motion? And they give you two coefficients. They give you coefficient of kinetic is 0.15, and coefficient of static is 40? I see it right? Yeah, it's 0.40. So, number one, or letter A, part A, what force is required to put him in motion? I forgot to mention, it's in the question, 59 kilograms is the mass of Happy. So, you need to know, first of all, if we draw a little diagram, his weight is pulling down on him. Now, he's not at any angle or anything. No, nothing is lifting him. Nothing's anywhere. Nothing's pushing down or lifting up on him. There's no other forces, just his weight. So we know that there must be a normal force equal to the weight force. All right, don't forget that's part of the problem in all of these. So first you'll find out Happy's weight. 59 kilograms times 9.81. I'll put it, okay, there. So what is that going to be? Why not pick 59? I could have picked an easier number to work with. Okay, 59 times 9.81, 579. 579 newtons is the weight. So therefore, the normal force will equal also. So how about the weight is negative 579, just because this is going down. So the normal force will be positive. See, I pretty much want to make that positive, the normal force positive, to not have to deal with any negatives in this. But 579 will be the normal force, okay? Because normal force equals opposite of the weight force. In this situation, it's not always true, but because if Lily was riding or stood on her back, or if you were lifting up on him a little bit. In fact, that's another thing. Moving a refrigerator, moving something really heavy, it's strange. Sometimes it might be hard to get it just in motion. Because you remember, it's hard to just get the thing moving. Once it's moving, you're okay. You can keep it moving. So what you can do is let's just say you get a bunch of people around it and they have a hard time getting it moving. If they were to lift up on it, even if they don't lift it off the ground, but just lift up to lessen the weight, lessen the normal force, now it will become easier to push it as well, to get it moving, and then once it's moving, the lower force can keep it moving. So lifting up an object, or lifting up, like you can't see a chair here. You can see, you can't see the top of it, but like I could pull some arms. Right now I'm lifting on it. It's not leaving the ground. I'm just taking the weight of it. You can see a little bit of the chair. I'm lifting up the weight on it. It will be easier to push when you lift up on it. Somebody else can then push, and they can get it moving easier. So because you're lowering the normal force. All right. Well, anyway, okay. So normal force is negative weight in this one, 579. So now the friction to get him in motion would be mu s Fn. So mu s, and by the way, I didn't draw it on there, but the friction force will be going in that direction. Okay. The friction force will equal 0.40 times 579 newtons. So what is that going to be? 232 newtons. So the static friction is 232 newtons. That's how much force is needed to start Happy in motion. Start Happy in motion. 232. Actually 230 if I do my sig figs. I don't know why, but a lot of times coefficients of friction are written with just two decimal numbers. Oh, we're still going to need to know the normal force is 579 for the other part. I'll just erase that little bit. All right, then that was A, letter A. Sorry about that. A, if you want to write that. Then A part B says, well, that question, the wording is messed up. It's a typo. If Happy is sliding across the ice ground, what force is required to keep Happy moving at a constant speed? So first we get him in motion by putting 230 newtons on him. He starts moving. Yay! Okay, he's moving. But then, if you want to keep him in motion, you only have to go to the kinetic friction. So 0.15 times 579 newtons is going to be 87 or 88. No, it is 87. 87 newtons. Wow, a lot smaller in this case. So only 87 newtons are needed to keep him moving. So as long as you run behind him and you're pushing it with 87, he'll keep moving. If you stop and he stops, now to get him moving again, you got to add 230 newtons just to get him moving. Then you can go back down to 87. Okay, that is all for number 4-9. Now, if you really wanted to, you could pause the video and you could do number 1 on the worksheet already just based on that. Now, I probably should have added some other questions in here because we're going to jump to some kind of crazy stuff here. I don't know if I would want to add one. Well, let's just think about this for a minute. The kinetic friction. Let's look at kinetic friction for a moment. I just want to show you a little thing to think about. So I drew a picture of F friction here. And let's just say it's 87 newtons. Say he's moving along. Okay, he's sliding along. Yay. And then let's just say that someone is here. Well, how about that? I don't know. Maybe Lily's over here. We'll draw her. Lily is back here running backwards. I want a pet seal to take home with me. And so she's got a rope tied around him or whatever. She's pulling him. She's running this way. Okay, so she's putting a force on Happy right now. We'll just call it the Lily force. Force Lily. She's pulling Lily this way, and friction is 87. So, okay, here, I wanted just to tell you this because it'll help a little bit in the next section. Right now, if Lily pulls, does she have to pull? All right, he's already moving, and she's moving. So what force does she need to keep him in motion? She only needs to put a force of 87. If Lily's force, okay, the net force on Happy will be the force of Lily pulling plus the force of friction. Here's what I want you to see. Net force, this is an important thing that will come up in the next part. Net force on Happy is the force of Lily plus the force of the vector sum, the friction force. Now, friction is negative 87. It's always opposite motion. So Lily's force has to at least be 87. And here's the thing, two scenarios. If Lily is pulling at 87 positive, so she's pulling 87 this way, friction is negative 87, she's pulling positive 87 this way, then there will be zero net force. Notice that. The net force, does that fit? Yeah. The net force is 0. Well, if the net force is 0, that doesn't mean it stopped. It just means it'll keep moving at a constant speed. So, if you're overcoming and equaling kinetic friction, the object will move at a constant speed. If you pull the exact force of the kinetic friction force, you will be pulling it along at a constant speed. That means it's not accelerating. In fact, net force is equal to ma. Remember that? So, mass times acceleration would be the force of Lily in that. So, if mass times acceleration is 0, then that means that there's 0 acceleration. I mean, the mass did not go away. He still weighs 59. Okay, so you're going at a constant speed. If the friction force and the pull force, or friction force, pull and push force, we'll call it push for behind pushing or pulling, if they're equal, then it moves at a constant speed. But now, what if she moves greater? Let's just say she pulls at 187 newtons. Okay? Well, now, if that's 187 minus 87, then the net force is 100 newtons. So now, he has a 100 Newton force. What that means is he's going to be getting faster and faster and faster and faster and faster. As long as the force is on him, he's accelerating now. Okay? So she might do it for a short time or for a long time, but she'll get him. It's just like if you pull someone along and then you start pulling them faster and faster, real fast. Okay. So anyway, this kind of shows you how could you find the acceleration. So the net force is equal to the pulling force of Lily and the friction force. You got to put in whether they're positive or negative, the vector. Then MA would be that. So if there was one positive 187, 100 newtons would be the force. So that means MA. That means I can calculate the acceleration of Happy. If I plug in his mass, 59, it'll be 100 divided by 59, whatever that is. This actually is not a bad example, 100 divided by 59. So he could be accelerating at 1.7 meter per second squared. 1.69 is the acceleration. So Happy will be accelerating that way, getting faster. Okay, now that is not needed to do number 1 on the worksheet, but that, if you've seen this, will help you a little bit in some of the things that are going to happen in the next 2 problems. So, let me try and do this one. And let me see how my time is doing. Yeah, I'm doing all right. I didn't know if this video was going to cut off, but hopefully it will not. Okay, so here under 410, friction force, inclines, and uniform accelerated motion. I wrote some equations in there, F parallel, Fn. I'm going to show you that, but I don't know if I really like them that much. I might want to just show you a net force equation, as I was showing you a moment ago. Let me just jump all the way to letter A down here. And it says, Critter slides a 2 kilogram box down a 51-degree inclined plane. I've got a 51 degree is theta. And it says Critter is going to slide a box. So somebody, I don't know who that is going to be. Maybe this guy can be Critter. I don't know why he would slide it, I guess, except maybe there's a little bit of friction there and he's having to overcome it, whatever. So he's pushing this box, 2 kilogram box. What a weird problem I picked here. Down a 51-degree inclined plane. So obviously it won't slide on its own, so he's got to push it, okay? Calculate the acceleration of the box. All right, so here's what we do. What will be the box's acceleration going down this? Well, first of all, we know when you see a problem like this, calculate everything that you know how to get. So I'll kind of go step by step. Number 1, I know, we can use another color if you want to. Well, let's find the weight of the box. So we know that the weight is pulling downward. We know that he is pushing it with a force this way. He didn't talk about what force he's pushing it with. But anyway, the weight is pulling down. So the weight of the box, mg, it'll be, let's put it to the side here, just take less space. 2 times 9.81. So that's going to be 19.7. Well, or 20 actually. I can stick at 20. Be easier math too. 20 newtons. Okay, negative 20. We'll put a negative. So the weight is negative 20. That means the normal force will be. We can't get the normal force that way. Remember, we got to make our little triangles. So we'll draw the perpendicular as a normal force, and then you got to come out this way. 1, and that one goes down. And here's that's theta, also 51. Okay, so we know that the normal force will equal Fy. So Fn will be the one going up there, whatever. The normal force will be cosine of theta times the weight. So we'll say this. Cosine of theta is equal to the normal force over the weight. Make sure I don't do it backwards like I did in that one video. All right, cosine of 51 equals, we don't know the normal force. I mean, it's technically Fy we're finding, but Fn will be the positive side of that. And F weight is 20 newtons. So 51 cosine times 20 is 12.6. or just 12, or 13 actually, 13. Only got 2 sig figs there. 13 newtons is the normal force. Force N. Sometimes I have seen normal force written as N, but that would be kind of crazy too. So, all right, so normal force, take that Y off of there. The normal force is 13 newtons. All right. Now, what was the question? I'm trying to go back here. Oh, better A, if they give you, if point 40 is the friction, calculate the acceleration of the box. Okay, so we know the normal force. We need to also know this force right here. And this is the one that I called force parallel, and I called that one once force perpendicular here. But you know what? That might just be unneeded in the notes. This is Fx, Fgx. The only thing, all right, besides the guy here, Critter, gravity is pulling down. But obviously gravity is not enough to get it moving, so he's going to have to add some more force to get it in motion. So gravity is pulling down with what force? It'll be Fx. Let's not call it F parallel. I'll call it Fx. I'm going to go back to what I've been teaching so far in the videos. Fx would be the force parallel to motion. That's what gravity is doing to pull it down. And so that'll be sine of 51 will be Fx over 20. So if you can see that one there. So 51 sine is 0.78 times 20. That's 15 or 16 newtons equals Fx. So, normal force, 13 newtons. Fx pulling down here is 16 newtons. Now, why do we need all this? You'll see when we put it together in a moment. They didn't ask for that one yet. But A, okay, what will be the acceleration? If mu k equals 0.40, then that tells us our friction force is going to be mu k Fn. So it's going to be 0.40 times the normal force, which is 13. I'm going to probably have to erase this in a moment. I'm going to run out of space. Well, visible space for you to see. So 0.40 times 13 is 5.2 newtons is the friction force. Okay, so again, the goal here is, what is the acceleration of the box? If the box is accelerating, I guess obviously it will be accelerating. Okay, so here's the two things we've got to look at. Let me get another color. That's one good thing about the chalkboard. It's got the colors here. So Fx, gravity, is pulling, that's the orange one, pulling it down, we'll say. Okay? Meanwhile, friction is acting this way against the box. And then it says that he is sliding the box down. This is kind of a weird question. He doesn't really have to do anything. He's not putting any force on it. He wouldn't need to. We'd need to know his force if he were, but it's not going to need his sliding at all, because look at this. Friction is 5.2, but gravity, Fx, is 16. Gravity is going to overcome that. So you know what? This question's kind of weird. If he had been putting another force on it, then we could add that force to it, but we can kind of disregard him. So I think it's more like he's just kind of holding the box as it goes down to guide it, but he's not actually putting any force on it. So I should say, instead of Critter slides the box down, you could change the word in that question to he guides the box down, guides it. He's not going to be putting a force. So we want to remember 16 and 5.2. So here's how it works. To make a net force equation, the net force on the box will equal Fx, whatever it is, positive or negative, plus the friction force, which we know is negative. All right? So let's put in Fx is 16 newtons. We'll let down be positive, and we'll let up be negative here. And so friction is going against it, so it's negative. 16 newtons for Fx. Friction will be negative 5.2 newtons. Okay? Then we can find the net force is equal to 16 minus 5 is going to be 11,